Okay, good morning. Today is April 22nd. This is a lecture on the deep learning course being given remotely at the Indian Institute of Science, Bangalore. Due to the coronavirus, all the lectures are being done on Zoom and on Facebook. So today's lecture is on a topic called autoencoders. We covered a related topic called linear factor models on Monday, the last lecture. Today is the second of the lectures on the research part of deep learning, and it's on autoencoders. It's an important topic. It comes off looking at like a fairly simplistic idea of coming up with a compression scheme for data, but it's much more than that. So it's quite an extensive topic. I was debating whether it would take us one lecture to do it or two. We'll see how it goes today. My guess is it's going to take 2 lectures to cover this rather important topic. So let me give some intuition behind what autoencoders are about. So as the name indicates, autoencoder is something that involves self. It says, is it possible to take an input and feed it to a deep learning network and produce the input at the output, and along the way produce some kind of encoding in between? So you would like to compress it and decompress it, just something like data compression. But it's more than data compression. Data compression, we want faithful reproduction. We have a huge file. We want to compress it so that it occupies less space on disk and then reconstruct it. That's what data compression is about. Autoencoding also serves a similar purpose. We want to go from a very high dimensional data to something manageable. And it should be such that it's possible to almost reconstruct what we started out with. Difference is that here we are not so interested in faithful reproduction, but we are interested in capturing the essentials, like essential features, if you will, of the input data. So in a sense, an understanding. So it's as if we want to come up with a description. And if one produces a good description of a scene or text or whatever input you have, it is capturing what is going on. And then it's good enough to reconstruct it as well. Maybe another analogy is if someone is telling a story, you not only want to capture the gist of the story, the gist should be so good that someone listening to the gist is able to reproduce the entire story. I guess it's a task of summarization. So it is that kind of a task we're talking about. And it's a pretty interesting topic because what we're going to summarize it by, I mean, it's going to be done by a deep learning network. The number of input units are as large as the number of input data points, such as, let's say, the number of pixels in an image might be the input, which is like 1 million pixels. And we are reducing into a few thousand elements of a vector corresponding to this encoding. And that encoding is also being done in such a way so that we can reproduce the entire 1 million pixel image if necessary. But we lose information along the way for sure. And we actually want to lose some information. We don't want to capture unnecessary details. So that is the objective here. And what happens here is, let's say we're going to train this network. It's going to be a deep learning neural network. And what kind of neural network machine learning task is this? It's an unsupervised learning task. It's not a supervised learning task where We take an input and the output is a class, such as an animal or an object. Those are supervised learning tasks. In an unsupervised learning task, we just have some data, presumably of all of relevant to some task. Maybe these are all pictures of animals, or all pictures of cats, or all pictures of celebrities' faces, so on. We want to capture what is essential in them. And essentially, we'll be mapping from a very high dimensional space to some tolerable size of space, a few thousand elements. And we're going to capture it in that way. So basically what happens here is, in that large dimensional space, there is a much lower dimensional surface or manifold on which we are capturing all of the data. And when we make some changes from in the input, a little bit here and a little bit there, that makes some logical sense, we're just going to be moving along what we call as a manifold in this lower dimensional space. So all of this discussion on autoencoders is about how we create these low dimensional representations, and how can we induce some properties into it. And they become very powerful tools as we move along. Autoencoders lead to an important topic called variational autoencoders, which can be used to generate very interesting pictures and scenes and so on. So anyway, we got to build that up by first learning about autoencoders. So I'm going to begin my lecture by showing an example of human faces being captured and how they might be on a manifold. And then we'll look at the mathematical formalization of the task. So I'm going to move to my slides. Okay, so hopefully you're able to see on the screen these slides called autoencoders, right? So let me just move to the first slide of this deck. So what we're going to do is we'll begin with what is an autoencoder. I gave you a sense already what an autoencoder is. And then there are many variations of this topic, like undercomplete autoencoders. This is by purpose. We are going to make these autoencoders lose information. So we don't want to retain all the information, which means it's not complete, it's undercomplete. And I mentioned why. We want to capture the essentials of the data, or an embedding, the same concept as embedding. And we bring in after complete autoencoders, the next topic is regularized autoencoders. Just like regularization is a standard topic in linear classification, linear regression, which is a way of introducing some prior knowledge into the task. And we do that in classification and regression. We bring in regularization for with many motivations. One of which is that we don't want too complex a representation. We want a fairly simple representation. We don't want a very high dimensional representation because it might be overkill, might be overfitting. So there are so many reasons for regularization in linear classification, linear regression. Just like that in autoencoders, we have regularization. So we'll talk about what kind of regularization, because we state the problem as an optimization problem. Once we state that as an optimization problem, its next step is to introduce regularization. After that, we speak about representational power, layout, size, and depth. And here we bring in an important concept called sparse autoencoders, saying we want as few parameters as possible. That's the idea of sparsity. And how do we impose that criterion in it? And then after we move, after representational power, layout, and depth, we move to stochastic encoders and decoders. In the beginning, we state the problem as a deterministic problem. We go from million dimensional space to 1,000 dimensional space. That is okay. But in stochastic encoders and decoders, we say, well, we are going to reduce the dimensionality, but it's going to be probabilistic. There is some probabilistic element in it that we are going to have a distribution rather than a single value. The same classical idea in Bayesian statistics, where we don't want a point representation, but we want a distribution. So the answer is not a single value, but it says it's a distribution. It's got a mean and a certain variance. It could be any answer in this distribution. So that seems like a more general way of answering any question without a single answer, but giving a range of values and what is the most likely value. And after that, we go into something called DAE or denoising autoencoders, where we bring in an element of noise into what we are encoding. So simultaneous to the encoding and decoding process, we tolerate a degree of noise. So that's another improvement. And then we go into contractive autoencoders, which is again contraction of the amount of information. So we'll cover some of these things today. Okay, moving on to the next slide. So here are a few simple illustrations of what an autoencoder is. Okay, so there are three different instances that are shown here in these pictures. So first of all, the slide says a neural network trained using unsupervised learning. So keep in mind, it's also a neural network with an input and output. In classic supervised learning, we have an input. In this case, take the first example, your cat as input. And in supervised learning, on the output side, we'd have 10 possible classes and say, is it a cat or a dog? That would be supervised. In unsupervised learning, there's really no label. We just have pictures of cats. So the way we are using it here is the input is a cat and the output is the same cat. And the information is now getting compressed from the cat representation and cat representation on either side to some intermediate representation. That is the encoding. So we are learning basically an embedding in some latent space. You can think of that as latent. It's not observed space. Latent. Observed space is the left and the right. Latent space is something in between. So we are mapping the data into this latent space. Well, this could be the representation for pictures of cats, or it could generalize to pictures of animals. And here we have perhaps a particular individual or a whole set of comedians or whoever you. And then we have an encoding, and the encoding here is shown in binary black and white values of some vector. And then there's the decoding to reconstruct it as close as possible. So it could be cats images, it could be people's faces, or it could be handwritten digits. Here we're encoding the digit 2, and then we want to reproduce the digit 2, and we go through an encoder, and we reproduce by decoder. In between is this compressed representation. So these are autoencoders, perhaps the same autoencoder, each time it is trained with different data sets to produce different types of representations, hidden or latent representations. So the representation in between, we can refer to that as an encoding, or in neural network terminology, we can refer to it as an embedding. An embedding is a low dimensional vector with fewer dimensions than the ambient space. So we refer to it as ambient space. This is ambient space of the face, of which the manifold is a low dimensional subset. So this could be a million pixel representation, and this might be a low dimensional representation. Of course, every face would be a different point in this low dimensional representation, or every cat image would be a low dimensional representation. And when we have enough of those examples, they would form some kind of a continuous manifold, because from one to the next, there is some continuity, very little change from one to the next. So it is now building a whole manifold of maybe 300 dimensional or 3000 dimensional space. So the embedding algorithm maps any point in ambient space X to its embedding H. And embeddings of related inputs form a manifold, right? So this is what's going on. This next slide shows a little bit detail about the nature of these manifolds. So a manifold in ambient space is an embedding mapping from X as the input to a lower dimensional H. There's a latent input, H for hidden. And this is showing, let's say we had the famous MNIST handwritten digits, which are 28 by 28 images, grayscale images. I think it was maybe black and white images, 28 by 28. So there are 784 dimensional representation for every handwritten digit. So we have a whole set of images, such as in this case showing nines. And rather than have them all in a 784 dimensional space, we have projected them onto a two-dimensional space here so that we can view it. And we see these 9 images all going along a particular curve here. Slight changes from one to the next. I think they're just being pulled down and down and down and down and down and down, perhaps. And how in this two-dimensional space, they trace a particular curve here in this low-dimensional space. And we refer to that particular curve as a manifold. So all these 9 images, with slight transformations from one to the next, trace a manifold. Here is a more interesting one. This is a little bit more imaginary. Okay, this one was exact, about 9s in a particular pixel representation. Here we have, let's say we had images of people's faces. Here is the first face here. Here's the first face here, and here is the first face here. So we go from a very high dimensional representation. This is a color image. And we are mapping it into some lower dimensional space. And then looking at it from that perspective and say they are all, this is a point in this lower dimensional manifold M. And if we keep changing this face a little bit, they're subjecting it to what's called as progression in age. This person is aging and aging and aging. So this is the query. And if we ask a question, what does that person look like in 5 years from now, 10 years from now, 15 years from now, like that. All those are all points on this same manifold. Similarly, here is a person, query is this person here. What would the person look like if the person was younger and younger, 5 years younger, 10 years younger, or 5 years older, 10 years older? Similarly, this lady here, this is the query, and we say 5 years younger, 5 years younger, and so on. So you can see that these kinds of images that are very related to each other, because they're all pictures of faces of people, and one picture to the next picture may have some relationship, and in which case they trace some lines within a manifold. So these are the kinds of manifolds that the deep learning network is able to capture. So it's all a question of what are these manifolds? What are some properties? How can we use them in a good way? For instance, we could use it for a generative model. We could say, what about a point somewhere right here in the middle, which is none of these 3 people? And then we use it and give it to the decoder. The decoder will decode it the same way it has been decoding and says, hey, there is another face. But that might be a person who doesn't exist, who could be an average of all the faces around it. But it'll have all the kind of complexities that all these other faces had. So you could use it as a generative model. We could use it to sample this manifold. So generate new faces, or if they were all of pictures or of whatever it is, right? Design of buildings, you can have new buildings generated from this manifold. New, if they're all photographs of plants, we can generate new plants and whatnot. So this can be useful for such tasks. But anyway, we're here to understand the mathematics of autoencoders can be used to do this. So the general structure of an autoencoder, it maps an input X to an output R. So this is the input on the left side, R on the right side. Along the way, we have an H. So it is a hidden layer H that describes a code used to represent the input. So the network learns two functions. One is f of x. F of x is equal to H. That's called the encoder. And a decoder that produces a reconstruction, R is equal to G of H. So F is the encoder, G is the decoder. And so we need to learn these functions. And remember, a neural network, all it is a function represented by the network. So that's the nature. The weights define the functions F and G. So we want to say something here about autoencoders, how they differ from general data compression. So autoencoders are data specific, that's only able to compress data similar to what they have been trained on. So if you are systematic in what it is you trained it on, it captures the features of that. If they're all cats, yes, it will capture that information, or dogs. But what if you mix them up with variety of images? It'll learn whatever is common to all of them, which might be kind of meaningless. It might end up capturing just something in common, like the background is similar or something. But anyway, autoencoders are data specific. But that is different from things you might have heard of or used regularly. We know of MP3 or JPEG, MP3 for sound and JPEG for images compression algorithms. They are different in that they make general assumptions about sound and images, but not about specific types of sounds and images. So they are general. You can feed to a MPEG any music and it will compress it for you and produce it almost with high fidelity. And similarly, a video can be reproduced with JPEG. But an autoencoder is specific for something. Like autoencoder for pictures of cats would do poorly in compressing pictures of trees, because features it would learn would be cat specific. So you would specifically build a program. It's been trained and is ready to go. And that's an autoencoder for cats. It's not an autoencoder for trees. Whereas JPEG would be a general one. So this has learned something specific about cats. Now autoencoders are lossy, unlike MP3 or JPEG. These are specifically forced to be lossy, which means that the decompressed outputs will be degraded compared to the original inputs. MP3 and JPEG would not tolerate such a loss, whereas autoencoders are designed to be lossy, because we want to learn the essence. What is it that makes it a cat? Right? And we don't want to be so lossy that we will lose all the information. We want to be able to reconstruct it back to some extent, but we're forcing it to say, tell me, what is a cat all about? You would say, oh, cat has whiskers and cat has eyes and it's got pointy ears or something like that. It's captured such basic things that we might think about a representation which is not accurate in every sense, but it's got a understanding. So that's where the intelligence comes in here. And the autoencoders are learned. So what does an autoencoder learn? So if we designed it such that g of f of x equal to x, you remember f of x was the encoding function and g of x was the decoding function. So if we take f of x and feed it as input to g, so it becomes g of f of x. So that should be back to x. We started out with x and we're coming back to x. If you're able to learn such a function encoder f and a decoder g, we're saying it's not going to be that useful. Autoencoders are designed to be unable to copy perfectly, restricted to copy only approximately. But in this process, autoencoders learn useful properties of data, being forced to prioritize which aspects of the input should be copied. So that is the essential description. And they can learn stochastic mappings as well. They can go beyond deterministic functions. So like f of x is a deterministic function. gives you exactly the same value, or G gives you the same value every time. Whereas we can also have non-deterministic or stochastic functions, where the encoder is a P encoder of h of x. What it's saying is, given an x, it's not going to give you a value of h, it's going to give you a distribution of x. We call it as the probability distribution P encoder of h of x. Similarly, given in h, which is the latent representation, we get a distribution of x in the decoder. So you can generalize from deterministic encoders to stochastic encoders. So a little bit about autoencoder history. They've been part of the neural network landscape for decades, autoencoders. That's just sort of the curiosity in the early days, saying, okay, here is something, you make it learn itself rather than learn what it is, what kind of object it is. Seemed like not a useful task. It's just learning itself, but that turns out to be powerful for these unsupervised learning or generative models. It was useful in the past for dimensionality reduction and feature learning. You're saying a 1 million pixel image is too much of data. Can't we reduce the dimensionality by some and then work with them for whatever we want to do, such as classification? So you can think of autoencoder as simply a dimensionality reduction method in the early days. And then there was a theoretical connection made to latent variable models and onto generative models. Generative models is to generate new data, new images, new text. And it turns out these latent representations are useful. And then along came a stochastic method of dealing with distributions, and not just deterministic autoencoder, but probabilistic autoencoder. And it comes along with a name called variational autoencoder. The term variational comes from a style of calculus called variational calculus, where we are dealing with finding not just like simple things like maxima, minima of a function. We are talking about, among all possible functions, which is the best possible function. So the argument or the output is no longer a value, but the output is a function. So it's called the calculus of variations. That's where the variational idea comes in. So it says, let's get the best possible distribution among all possible distributions. Just like we're saying, get the best possible value in maxima, minima. Here we say, what is the best possible function? So anyway, it's going to be a bigger topic, variational autoencoder, when we get into generative models. Right now, we're only on autoencoders, and it's worthwhile to have a slide on this thing called variational autoencoders, just to know where we're going to be going. First of all, let's again look back at the basic autoencoder. This one is written bottom to top. The encoder is at the bottom and the decoder is at the top. The encoder F is taking a human face image and multiplying it by a weight matrix, W1, bringing it down to a lower dimensional vector, a 2000 dimensional vector, multiplying it by W2 to give a 1000 dimensional vector, multiplying it by a W3 to give a 500 dimensional vector, multiplying it by a W4 to give a 30 dimensional code layer. So by going through this process, we are somehow systematically reducing the information, and we're bringing it down from a many dimensional image to only a vector of 30 elements. Saying, here is my compressed description of that. And you have specified you can only give me 30 units, and I'll bring it down to 30. And then that same 30 is being decoded into 500, into 1000, and into 2000, and back to an image. This image is shown here, a little bit blurry version of the original one, saying we have lost some information along the way, but it's not too bad, we can recognize it. The important thing was not that we got this decoder value back. We don't care about that one. We care about this one in the middle, which is 30. It says, oh, okay, you've learned what this face is all about. And we can move around that 30-dimensional vector, and if we can go to change the values a little bit this way, that way, we're going to get new faces, so on. So that is the essential representation. And how do you get all these weights, W1, W2, W3, W4, and then you have W4 transpose, W3 transpose, W2 transpose, W1 transpose. They're using the same one here, but need not be the same one in transpose version. And these weights W are learned using training samples. We are feeding a lot of these and then comparing the result with what it should have been, and says, look, it's not a very good description or very good output you provided. It's not so close. So, well, go change the W's, 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 W's. And you keep on going back and forth and do it over a whole data set until you minimize a loss function. A loss function measures how close the output was and how close it should have been. And that's what we obtain. Okay. All right. So these are autoencoder training methods. Autoencoder training methods are just like any other deep learning method. Is a feed-forward, non-recurrent neural network with an input layer, output layer, and one or more hidden layers. Can be trained using the same techniques. Compute gradients using backpropagation, followed by mini batch gradient descent. Unlike feed-forward networks, there is something called recirculation, another method, where we compare the activations of the input to activations of the reconstructed output, something more biologically plausible, but not very much used in machine learning. So let's begin with these special topics within autoencoders. Now that we know autoencoder is all about compressing information, let's cover some specific topics here. And I already mentioned what is meant by undercomplete autoencoder. We are computing input to output, and simply copying input to output sounds useless because we have no interest in the decoder output. We hope that H takes on useful properties. So we want H to have lower dimension than X and force it to capture most salient features of the training data. So that is the important thing, the saliency. So how do we set up the training of an autoencoder? It's pretty straightforward. We have a loss function, L of X of G of F of X. You can imagine what this is. Is the loss associated between taking X and subjecting it to the encoding function and then subjecting a decoding function. It gives you something, some other X tilde we can call it. So the loss of X tilde is, what's the difference between this X and X tilde? How different are they? Where L is a loss function penalizing G of F of X for being dissimilar from X. And the kind of loss function could be an L2 norm difference, mean squared error. We could simply compare pixel by pixel X and X tilde and take the value differences and square them and add them up, take the square root and say that is the value of the loss. And we want that loss to be as small as possible, ideally 0. When the decoder G is linear and L is the mean squared error. So G is linear, means only one layer here. An undercomplete autoencoder learns to span the same subspace as PCA. It says if you simply used one level of matrix multiplication, this is the same as principal components analysis, which is a famous method of simple data analysis and machine learning. So we have a much more powerful tool here than PCA. Autoencoders with linear and nonlinear F and G can learn more powerful nonlinear generalizations of PCA. Right? They can be more powerful, but we don't want very high capacity because it can just, if you give a many layers with many units per layer, you are giving it a lot of degrees of freedom. So it can learn the inputs in a rote fashion. So it's going to reproduce things exactly. And we said, don't give it too much capacity. Keep it hungry. It's kind of an interesting concept. So this diagram here, autoencoder training using a loss function, illustrates the straightforward idea of design of an autoencoder. F is mapping input X to H. X goes to H. G takes H and brings back X. It becomes an X prime here. And the loss function is argmin of f of s. Out of all the f's and g's, is a composition of f and g of x. So we're taking the squared difference between the two, and we're saying keep that as small as possible. Choose your f and g very carefully. All that means is choose all your weights of that define f and g as well as possible. So if we had one hidden layer, we would take input x in d-dimensional space, maps to output into some p-dimensional h, and then the h value is given by sigma 1 wx plus b. Recall that is just a simple a linear function. We also refer to this as logistic regression. It is simply multiplying x by a set of weights and then add a bias b and then a sigmoid that maps it into 0, 1. And x prime is also a sigmoid function. So this is for a black and white image. And we get 0, 1 values, or it gives you grayscale values too, 0 to 1. Okay. And is an element-wise activation function, such as sigmoid or relu. And it is trained to minimize the reconstruction error. We are plugging in L at x and x prime what it is. We have x minus sigma 2 of sigma 1 plus b. So that is the expression for the loss function. And the way we train it is take the derivative of the loss function with respect to the weights w, and we try to minimize that L, make it as small as possible. The only way to make it as small as possible is to keep on changing the w's until it approaches 0, and then we say, there's your set of w's, and that's what we need for training the autoencoder. So this is about encoder-decoder capacity. So if F and G are allowed too much capacity, capacity means how many layers, how many units per layer. The autoencoder can learn to perform the copying task without learning any useful information about distribution of data. I guess it's like telling people, if you have a photographic memory, you might be able to remember everything that the teacher wrote on the board or something, but you might have absolutely no understanding of anything that was said. So we'd rather not have a photographic memory. We would rather have an understanding of the issues. So that's what we're saying. Don't give it too much capacity. So an autoencoder with a one-dimensional code and a very powerful nonlinear encoder can learn to map xi to code I. Okay, that's just another point being made, that if there are a large number of indices available, then it can just label all the messages as a particular code number, right? This is like the telegraph system we used to have in India. So instead of sending a whole message like happy birthday, you would simply say, please telegraph code number 1. Code number 1 is happy birthday. And then code number 2 is, something else, some other message, many happy returns of the day. Or code number 3 is congratulations on your wedding, that kind of thing. So the messages can all be encoded by these numbers. And if you have a very large number of messages possible, if you give a very large number of code, then it can represent every one of the messages. So we don't want this kind of an indexing scheme. We want a true understanding of the message that is being said. An autoencoder trained for copying task fails to learn anything useful if the capacity is too great. So we don't want to have a way of exactly transmitting the exact message that would have full capacity. So somewhere in between of having a simple digit representation versus complete faithful reproduction, something in between. Essentially, it learns that there are certain types of messages and they have these properties. That's an intelligent way of coding. So cases where autoencoder learning fails is that they fail to learn anything useful if the capacity is too high, which is what we said. And the capacity is controlled by the depth. We're talking about deep learning. If you give it a lot of depth, capacity becomes high. And the hidden code H has a dimension equal to input X. Okay, so you are simply representing it by however many elements there were in the input. Or the overcomplete case where hidden code H has dimension greater than input X. So we don't want H to be so powerful that it's even larger than the input. So all this means it's got to be of smaller capacity. And to get the right encoder design, autoencoder design, we use regularization. That reminds us of simple idea of linear classification, linear regression, where we're saying don't overfit, don't capture every little variation in the data. That is why we bring in regularization. Ideally, choose code size, dimension of H small, and capacity based on the complexity of the distribution. And regularized autoencoders provide the ability to do so. Rather than limiting model capacity by keeping encoder decoder shallow and code size small, they use a loss function that encourages the model to have properties other than copy its input to output. So this says, rather than simply using that loss function L we just saw, L of X, comma, G of f of X, that was the loss function we used. So we add an additional term to it, plus some omega of X. Same trick we use for regularization in other areas. So before we define that omega X, okay. So regularized autoencoders have properties beyond copying input to output. So the regularization can have properties of sparsity of representation, smallness of the derivative of the representation, robustness to noise, robustness to missing inputs. So you see, these define a whole set of topics, subtopics within autoencoders. So we come across topics such as this is a sparse autoencoder, or this is something that can be trained easily, or this is something to do with noise, right? We saw a definition, of autoencoder robust to noise, and then even to missing inputs. And a regularized autoencoder can be nonlinear and overcomplete. All right. Oh, it can be overcomplete. So you can afford to have large capacity in your autoencoder if you take care that the loss function is not simply fitting, but bring in some other external consideration. So it is possible. And it can still learn something useful about the data distribution, even if model capacity is great enough to learn trivial identity function. So generative models is this one of the areas of excitement in all of deep learning, like generative adversarial networks or variational autoencoders. And they are all being viewed as special cases of autoencoders, and they go beyond regular autoencoders. Generative models with latent variables and an inference procedure. So normally when you think of generative models, we think of modeling the input. Okay, you give me a set of data corresponding to some class. These are all images of celebrities' faces. It will learn a probability distribution over all the pixels and say, well, there's the distribution. Now you can sample the distribution and gives you new faces. Whereas a system which has captured latent variables, what are the basic features and all that can do a much better job than at the surface level. So you just need latent variables and an inference procedure for computing latent representations given the input. can be viewed as a particular form of autoencoder. So a generative model which uses both the input values and the latent values. Generative modeling approaches which emphasize connection with autoencoders are descendants of what's called as a Helmholtz machine. These names from physics keep cropping up throughout machine learning, as you might have noticed, in deep learning as well, because they encountered all these things, statistical physics, they called it. They were also trying to model physical things. They were trying to model atoms. We're trying to model bits versus atoms. So modeling atoms, modeling bits, kind of similar enterprises. And so these generative modeling approaches, one famous one is the variational autoencoder, and we'll see briefly. And then another topic, generative stochastic networks. So before we go to variational autoencoders, let's look at these images here on the left side. Let's say we are interested in a particular feature about whether the person in the photo is smiling or not. So you look at this kid on the top, he seems to be showing some disapproval, not exactly smiling. So on a range of -1 to +1, we can say this kid's expression is more on the negative side in terms of smiling. So it's maybe -0.6, right? So they're giving a specific value to it, saying -0.6 is the value of the smile. Then here we have the famous Mona Lisa. You can't tell from Mona Lisa's expression whether she's smiling or she is frowning. So it is inscrutable what her expression is. So we can say can't tell. So we put that right at 0. It is neither on the positive side of smile or the negative side of smile. And then we have a third one. This kid is unmistakably very happy and smiling. So we can put this kid as being on the positive side. So this is a point estimation or a point attribution. The reason that's being given here is the latent representation figured out by the autoencoder is bringing it down to a few values. And it is not actually capturing all the pixels, but it's capturing something essential about it. One possibility is that it's capturing somehow that the person is smiling. It's one of those elements in its representation might be the degree of smile. One of it could be a vector corresponding to that particular feature. So this idea of variational autoencoder says, instead of giving point values to smile, can we work with distributions of these? So we can say, so this kid's expression is not a point value, but a normal distribution, seems to be centered exactly at this point. But it's allowing for that kid actually to be smiling with a very small probability, and could be even more frowning with a very small probability, but most likely frowning right here. And this one similarly is not a point, but it's a normal distribution, which is saying Mona Lisa could very well be smiling or frowning with lower probability than don't know, right? So this is a probability or a stochastic representation of the same feature. And similarly, this kid here has a distribution like this centered around this point. It's quite possible the kid's smile is even brighter, or maybe not so bright, but still smiling. So this is the idea of latent variables being treated as distributions. Seems like a much more powerful way of saying something rather than pinpointing something. You're allowing for different variances for each of these allowing it to show the uncertainty you have as to what to assign. And for instance, if we went to human evaluators and asked them to assign a degree of smile, some may give a value higher or some may give a value lower, but on an average, all their ratings will have a Gaussian distribution. But it will not be exactly the same value. Everyone won't give the same value. So this idea somehow comes into a famous autoencoder referred to as the variational autoencoder. And the VAE, variational autoencoder, is a generative model. What it does is it not only obtains an encoding, but it provides a distribution. And that distribution can be used to generate samples from it. So we can have these photos of cats, and it captures them. And when we provide any input, it gives you a distribution. And we can use that distribution to generate a sample, which gives you another version of it. It may not be exactly the same one. Okay. So it's able to generate samples that look like the samples from training data. With MNIST, these are the handwritten digits. These fake samples would be synthetic images of the digits. It's as if, and we can keep on sampling. We send in an input, and this autoencoder produces this distribution. And with that distribution, we can sample it again. That sample is being passed through the decoder. It gives you a 2 again. But it's got this peculiar thing. It goes from 2, the encoder output is a distribution. What? It's not got a value, it is a distribution. How do we deal with that? Due to random variable between input output, it cannot be trained using backprop. How would you train this thing with some distribution in between? Instead, backprop proceeds through parameters of the latent distribution. And there's a famous trick here called the reparameterization trick, that a normal distribution with mean mu and covariance sigma, diagonal matrix sigma, is given by mu plus sigma times n01. So what it is saying is a normal distribution can be represented using its parameters, which are discrete value, which are deterministic values. Mu is a mean, and then sigma is also deterministic. But you're using a normal distribution between 0 and 1, which is called the standard normal distribution. I can give you a sample from the standard normal distribution and poof, multiplied by sigma, which is a deterministic value, and add mu to it. Okay, it gives you exactly what a n mu sigma would have given. And this mechanism is shown specifically here in this diagram. So we are going from an input to a deep learning mechanism. And rather than coming up with some kind of Gaussian over here, it generates a mean and it generates the variance. This is the mu and sigma, deterministic values. And once we have the mean and the sigma, that is mu and sigma, we can use N01 to generate a sample from that. You sample from that distribution. And that is this vector here. And that is subjected to the same decoding mechanism to produce the output. So we are going here from 2. This part here where we had a Gaussian got replaced by the mean and the variance of this parameters here. So this is a standard deterministic network, and you can learn all the weights correspondingly. So VAE works like this. There's a whole chapter on VAE, so we'll be doing more of that. But I wanted to give you a sense. What is this autoencoder and what is this famous variational autoencoder? Variational autoencoders have been shown to do all kinds of beautiful things, such as train it on photographs of churches. They've input all kinds of outside of churches, and it learns all about it, and then it generates samples of new churches you've never seen before. They don't exist, but it has learned exactly what a church is all about, and it creates that. And similarly, they have trained it on scenes of bedrooms in hotels. Saying, here are all the layouts of how the beds and the furniture are kept, and train it on all these, and then use a variational autoencoder to generate as many samples as you want of photographs of new bedrooms that don't exist. Very powerful as a method for a deep learning network to do something very creative. And I've also seen floor plans. So you say, well, here are examples of floor plans of buildings, houses, right? You want to design a house. The floor plans, and then you say, learn from all of this, and then generate new floor plans. And you might put some restrictions on saying there's going to be square, or it's going to be rectangle, or it's going to be diamond, or what have you. Give me a new floor plan of laying out all the walls and where the WC should be, and so on. So all kinds of creative things can be done with this variation called variation autoencoder. I'll do one more thing in autoencoders. We won't be able to cover all of autoencoders today, but this next topic is sparse autoencoder. This says we don't allow all elements of the network to be active. Only a few nodes are encouraged to activate when a single sample is fed into the network. So we have an input layer, encoder, hidden layer, decoder, output layer. And only some of them are turned on and others are all turned off. Kind of reminds you of the dropout principle in standard supervised learning. We're doing unsupervised learning here. We are just learning something about the data, nothing about what it means. So fewer nodes activating while still keeping the performance would guarantee that the autoencoder is actually learning latent representations instead of redundant information in our input data. So this is saying by selecting few nodes along the way, one more way of learning interesting things. There's a whole lot of theory on this sparse autoencoder, as you can imagine. Really, just by preventing certain nodes to be activated, you can have very good representations. Why is that? So a sparse autoencoder is nothing but a regularizer. You see here, omega of h. This is just like what we had with supervised learning, in linear classification or linear regression. So the loss function is not, whatever loss function you want is this L. And then there is this omega of h. And this is a penalty, sparsity penalty. If h is sparse, then that penalty will be lower. If h is dense, the penalty will be higher. So this forces it to choose a lower sparsity. So sparse encoders are typically used to learn features for another task such as classification. So this is saying, I need a feature extraction method. And they're saying one way to do it is use a sparse encoder, and that controls how many elements you're allowed in your features. And then you're going to use that for learning a classifier. So that would be a classic use of it. An autoencoder that has been trained to be sparse must respond to unique statistical features of the data set. So this is saying, what are some unique statistical features? It must respond to them. So the sparsity penalty can yield a model that has learned useful features as a byproduct. Interestingly, the sparse encoder doesn't have Bayesian interpretation. That's the beauty of this deep learning is you cover all the early topics even when you come to a later topic. In fundamental machine learning, when we learned about classification and regression, we talked about the regularization term. which is a term applying to all the parameters of the parameters of the network. And then we impose on it, yeah, that is a regularization term. And then later on we learn, well, look, whatever that regularization term you used, you brought in some prior information, and that's exactly what a Bayesian model is. And when you use sum of squared errors and you use a simple regularization term, norm, it's called the norm penalty. When you bring that in, one can show it's exactly equivalent to having a prior distribution over the parameters that's Gaussian. Wow. So you are starting out in a frequentist approach, nothing Bayesian about it, no priors. You're simply using sum of squared errors, which is actually equivalent to minimizing the likelihood. And you brought in this regularization term, and the regularization term happened to be minimizing the length of the weight vector. And then we say that is equivalent to a Gaussian prior over the parameters. Okay, so coming back to this topic, which is autoencoders, the penalty term omega h is a regularization term. And the primary task of the network is to copy input to output with the unsupervised learning objective. Also to perform some supervised task. It depends on the sparse features. So in supervised learning, regularization term corresponds to prior probabilities over model parameters. And a sparse encoder doesn't have regularization, depends on the data here. Right? So the difference there is in the standard regularization, there was no dependence on the data because the term becomes log p of x given theta and log p of theta. It just depends on the parameters here. Whereas the regularizer here, h depends on the parameters. So it represents a preference over functions, and it is not exactly Bayesian, which is kind of very interesting mathematical insight. Okay, so it's a bit past 12 o'clock. I've been giving 1 hour lectures, so we're going to do this part on generative models use. And then we have sparsity inducing priors and so on, a little bit of Bayesian stuff here, and we go on to stochastic encoders, which we already saw some applications of it, denoising autoencoders, and then something more about the manifolds. Okay, that's will be one more lecture on autoencoders. Okay, we're going to stop at this point, and I invite any questions you might have.
Sir, I have a question.
Yeah, go ahead.
Sir, in the VAE, the variational autoencoder, so when we are trying to get an output from there, do we get some kind of a manifold? Can we like estimate it that way, that we are getting a manifold?
Well, when you say output, we have to be careful what we mean by the output. All of these
Because
variation autoencoders have 2 levels of output. If you say one level of output is just the representation, right? And
yeah, like full representation, yes.
Yeah, that is the representation. Now, when we apply the decoder to it, then you get back something, right? When you apply the decoder to it.
Yes, yes, yes.
So what are you interested in? Are you interested in the latent representation, or are you interested in just looking at the output?
Output. So
Yeah,
because we are getting a variation of what we had given as input, so we are getting a manifold related to that input.
Yeah.
Is it
that's
like
right.
meaningful?
That's right. So the output is something that is taken from a distribution. So there is a sampling going on here in the middle. You know? So yeah, we generate the mu and the sigma in between. So we input We input a sample, and then we get a mu and a sigma, and we use n01 to actually get a random sample. And that is what is used to run through the decoder. And so that becomes a particular sample. So the sample we get at the output, yes, it is a function of the input, and it is a function, of course, of all the weights that have been learned, right? So, but it's done here in a variational manner where we have a value for the mean. Just like that smile thing we had, we have a distribution for the smile as if, okay, what's the output? It says, well, I'm going to take it out of that distribution. This kid had a very uncertain smile, and we're going to give you a sample from that kid's smile, and not exactly what kids. So you see, they get the idea. So that's what we get, a sample from that kid's distribution, rather than a distribution over all of them together, right? That would not be interesting. So an input is being converted into a specific output in a VAE. Okay. Yeah.
Okay.
All right.
One more question is
Yeah.
you were talking about F and G. So if we get G as F inverse, would that help us or would that not help us?
Well, if it is exactly mathematically F is G inverse, it is not very useful from
Mm-hmm.
an autoencoder point of view, because you're guaranteeing me this is an exact inverse function. We're trying to keep away from exact inverse functions, which is why we try so hard to make it harder for the system to, to
Okay.
reproduce it exactly. So we don't want an exact inverse function. But anyway, those things are hard to get hold of anyhow, to get an exact inverse.
Then why aren't we using some different loss functions? Because if we are using some loss function for Euclidean distance or MSE,
Yeah.
so that will give us something closer to FNG, which we don't want.
Yeah.
Then we should use a different loss function.
Yeah. You know what happens is we're going to transition from all of this, from generative models. We're going to go into from VAE to GANs. And when we go there, you will see a whole range of loss functions people use to have all kinds
Okay.
of properties. There's what's called a Wasserstein GAN. And that uses a particular, and the Wasserstein GAN is based on what's called as the earth mover loss function. Very
Huh?
peculiar. Earth mover. It's about, think of each probability distribution as a pile of dirt, If you look at a
Okay.
construction site, you will have the sand in a pile. It's looking like a three-dimensional Gaussian distribution, the pile of sand in front of the construction site.
Okay.
So
Yes.
that's a Gaussian. And then it says, supposing there was another pile of sand next to it, that is also another Gaussian distribution. And we're asking the question, how similar are these two distributions? And then we say, well, how much effort does it take you to, how many shovels of sand would it take to convert one pile to the other pile? And if they're exactly
Okay.
the same size pile, then it's zero. Oh, they're exactly the same. Or they're so different that you will need a lot of work. So that is again a particular distribution. That's a measure of the distributions. You can similarly think about it. The model has a distribution for the data, and the data has a certain distribution itself. And are they one and the same?
Yes.
If they're one and the
No.
same, your model has captured exactly what the data says. If model has not captured it, the Wasserstein measure will say they're not the same. Well, then change the parameters until the distributions are the same. So they have tried many different ideas there. Wasserstein is the most famous of them, but there are other measures that people have used. But we are starting out at the elementary point here, what a simple autoencoder is. And so we started out with a simple loss function, but we move on to that topic. Okay. All right.
Okay.
Yeah.
Thank you.
Any other question? Okay, very good. So we will continue this lecture on autoencoders and wrap up some varieties of manifolds and so on. That's chapter 14 of the deep learning book. And then you can look up what chapter 15 is. I forget now. I think it's probably graphical models or something. Okay, so anyway, we are on chapter 14, middle of chapter 14 now. All right, have a nice day and see you next Monday.